The S2 sphere is in three-dimensional space and has dimension 2. In the same way, we can study the sphere in four-dimensional space. It contains all the points that are at the same distance from a center point. But now, to determine the position of a point on this sphere, we need three numbers. This means that the sphere has dimension 3, and of course we will call it S3. You will not be able to see this sphere in four-dimensional space because your space has only 3 dimensions, and the screen only has 2. I can only call upon your imagination. To get a better understanding of four-dimensional polyhedra, we can do just what the lizards did with the three-dimensional polyhedra. We first inflate them so that they lie on a sphere, and then project this stereographically onto the plane. This time we'll inflate the polyhedron until its faces lie on a hypersphere in 4 space and project stereographically back into our own 3 space. I'm going up to the North Pole of the sphere in 4 space, and I'll project it down to you in your 3 space. You can't see where I am. Just remember how the lizards couldn't see their kinsman right up on his viewpoint either. Now we're in exactly the same situation. Here's the simplex. You can see its 5 vertices and its 10 edges. Of course, in this view, edges are circular arcs. So now we have a situation like that of the three-dimensional polyhedra, projected stereographically onto a plane. Here's the hypercube. It's easy to recognize it from its 32 edges and its 16 vertices. Seeing things this way is so much easier than with the shadow method or the three-dimensional cross-sections. Here's the 24 cell, with 24 vertices and 96 edges. Finally, the 120 cell and the 600 cell. Let's add the two-dimensional faces to get an even better view. The simplex, with its 10 triangular faces. Of course, these two-dimensional faces are pieces of spheres, just as before when we saw that the edges were circular arcs. The simplex is spinning in 4 space, before being projected stereographically. Remember when the Earth was spinning like a ball, and we saw the motion of the continents? Now and again, a face passes through the projection pole, and the projection becomes infinite. It looks like it blows up on the screen. Let's take a quick look at the hypercube. You see that the space is divided into 8 cube-shaped zones. These are the three-dimensional faces of the hypercube. As for the two-dimensional faces, they are squares, though rather bloated and twisted. There are 24 of them. are my favourite, the 24 cell. Look at that. The 24 cell is really wonderful. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. 8 edges start at each vertex. Here's the 120 cell. Let's try to understand its geometry better. Four edges start at each vertex. The two-dimensional faces are pentagons. There are 720 of them. These 720 pentagons form 120 dodecahedra. Look at all those dodecahedra fitting nicely together. Isn't that amazing? Let's finish with the 600 cell, with its 600 three-dimensional tetrahedral faces, its 1200 triangular faces, its 720 edges, and its 120 vertices. Trust me, there are 14,400 symmetries of four space which preserve this object. Well, there you are, we're done with our first voyage into the fourth dimension. It's a dimension full of amazing things. Of course, the mathematician's imagination isn't limited to the fourth dimension. There are the fifth, the sixth, the nth dimensional, and even the infinite dimension. Each dimension has its own character, but it has to be said that the fourth is the prettiest. Why? Maybe because after all, it has a sort of physical reality. Einstein's relativity theory, dating from the early 20th century, postulates that space and time are somehow bound together into a four-dimensional space-time. A point in this space-time is an event, characterized by its position in space x, y, z, and by the time t when it occurs. Dealing with relativistic physics therefore requires an understanding of four-dimensional geometry. It is interesting to notice that the discovery of this four-dimensional geometry precedes by some 50 years the discovery of relativity. It's one of the many interactions between mathematics and physics that the history of science delights in.